Hello all, welcome to this channel cfdbaba. Here we simulate CFD cases using ANSYS Workbench. Today we will simulate flow of cold air over a hot sphere. To start the simulation, drag in the Fluid Flow Fluent option into your workbench. The CFD simulation is divided into three main parts, that is pre-processing, solving, and post-processing. In the pre-processing, we create the geometry and mesh it. In the Solution tab, we apply boundary conditions and solve the iterations. In post-processing, we visualize our results using different forms of contours, vectors, or streamlines. To start the simulation, we will create our geometry using Design Modeler. Right-click on Geometry and open Design Modeler. To create the sphere, we will select YZ plane. Click on Create. Click on Primitives and click on Sphere. Click on Generate. I will use the units as millimeters. Change the units to millimeters. Specify the radius of sphere as 50 millimeters. Click on Generate. Next, we will create an enclosure around this sphere. To create an enclosure, click on Tools, click on Enclosure. Click on Generate. This will create an enclosure of default size. Change the size of enclosure as following: 800, 200, 200. In the negative x direction, we will use 500 millimeters. In the negative y and negative z direction, we will use 200 millimeters respectively. Click on Generate. This will generate an enclosure around our sphere. The enclosure is designed such that the inlet length of the enclosure is shorter than the outlet length. The reason of this outlet length being longer is that we need to study the flow in the wake region, that is, the flow behind the sphere once it carries away heat from the sphere. Next, we need to model the fluid domain. We need to eliminate the solid sphere that is present in our geometry. To eliminate the solid sphere, we will use Boolean operation. Click on Create. Click on Boolean. Select Subtract operation. We need to select target and tool bodies. Target body is the body from which you want to delete the object. Tool body is the body which needs to be deleted. Select the respective bodies. Click on Generate. This will give you a fluid domain inside which the sphere has been cut out. You can observe that our geometry is symmetric about the XY plane. Click on Tools. Click on Symmetry. We will select the XY plane and click on Apply. Click on Generate. This will split your geometry exactly in the center and will provide you with the symmetric half of your geometry. You can view the hollow sphere cutout that has been made inside the fluid domain. The cutout of the sphere will act as a wall. We will assign temperature boundary condition to the sphere. The symmetric boundary condition reduces the geometry size into half. This reduces our mesh count and hence the problem is solved more quickly. Once the geometry has been prepared, close the design modeler. Right-click on Mesh, click on Edit. This will open the Meshing tab inside ANSYS Workbench. To create the mesh, click on Mesh and click on Generate Mesh. This will create a coarse mesh around the sphere. To reduce the size of the mesh, go in Sizing and then select Max Face Size and change it to 50 millimeters. Click on Generate Mesh. This will create a more finer mesh around our sphere, which will provide us with better results. You can view the mesh count in the Statistics tab. The number of elements in our mesh are around 15,000. Next, we need to give named selection for our boundaries. To create named selections, select the Face Selection filter. Click on the inlet face, right-click, and click on Create Named Selection. Type in the name as inlet. Make sure that the flow is going in from the negative x direction and coming out from the positive x direction. Next, we will assign symmetry boundary condition to the symmetric face. You can press N, which will directly take you to the Selection Name tab. Type in the name Symmetry. Make sure that you name it correctly. Click on OK. Select the walls by pressing the Ctrl key. Press N. Name it as walls. Select the outlet face. Press N. Name it as outlet. You can check your named selections from the named selection tree. We need to select the sphere. Press N. Name it as Hot Sphere. Click on OK. This will ensure that all the boundary conditions are present in the Fluent tab. Once the named selections are completed, right-click on Mesh and click on Update. Once you get the message, close the Meshing tab. Right-click on Setup, click Edit. We will select Double Precision and I will use Parallel Computing. I believe my laptop has 4 cores. That's why I will select 4 processes. Click on OK. Parallel computing helps you solve your problem faster, but if you keep it running for a prolonged duration of time, it may take a toll on your system hardware. Once the mesh has been imported into the Fluent tab, Click on General. Select the gravity. We will assign the gravity in the negative y direction. Enter the value of minus 9.81 for negative y direction. Go to Models. Double-click on Energy and turn on the energy equation. We need energy equation when we are solving problems related to temperature and heat transfer. Double-click on Viscous Laminar and select the turbulence model. We will select K-epsilon 2 equation standard turbulence model. Click on OK. Next, we need to assign the boundary conditions to our boundaries. Make sure that the material selected is air for the fluid. Double-click on Boundary Conditions. Select Inlet and make sure that the type is Velocity Inlet. Click on Edit. Enter the value of 1 meter per second for the inlet. Select Hot Sphere. Make sure the type is Wall. Click on Edit. Here we will assign temperature to the sphere. Click on Thermal section. Select the temperature thermal condition. Enter the value of temperature as 473 kelvins. Click on OK. Make sure that the type for symmetry is Symmetry and the type for outlet is Pressure Outlet. Double-click on Methods. Here we will use coupled method with second-order upwind scheme. Double-click on Initialization. Click on Standard Initialization and Compute from Inlet. Click on Initialize. Once the initialization has been done, double-click on Run Calculation. Enter the number of iterations as 100. Click on Calculate. This will start calculating our results and a residual graph will appear on the screen. Residual values are nothing but the difference between calculated values and actual values. We want the difference between actual and calculated values to be as less as possible. Generally, magnitude of 10 raised to minus 3 is acceptable in many CFD cases. Make sure that the residual graph is going in the downward direction. This means that our problem is converging. Once the iterations have been completed, you will get Calculation Complete message. Click on OK. The next step is to view the results that have been generated by the software. Go to ANSYS Workbench, right-click on Results, click on Edit. First, we will view the contour of flow over our hot sphere. To view the contour, first we need to insert a location. Click on Location, then click on Plane. Click OK. We want our plane in the XY direction. Select the method as XY plane. Click Apply. ANSYS automatically creates a plane at the symmetry boundary condition. Now we need to plot our contours over this plane. Click on the contour button. Click on OK. Select the location as plane 1. This is the plane that we have created. Select the range as local. Click on Apply. Go to Render and turn off the lighting. Again, click on Apply. Turn off the plane 1 view. We can increase the number of contours up to 110. Click on Apply. You will see that the contours have become more smooth. Here we are able to view the pressure contour. The flow of air is from negative x direction towards the positive x direction. Click on Variable and select Velocity. Click on Apply. Here you can view the velocity contour. Double-click on Legend Default View. Click on Appearance and select Fixed Method. Click on Apply. This makes the legend more easier to read. Double-click on Contour. Select the variable as Temperature. Click on Apply. Here you will be able to see the heat transfer between the hot sphere and the cold air. To clearly visualize the effect of this heat transfer, we need to select the range as user specified. We will enter the minimum value of 300 Kelvin and maximum value of 305 kelvins. Click on Apply. Now we can visualize the heat transfer that is taking place between the hot sphere and the cold air flowing over it. You can clearly visualize that the heat is getting carried away from the sphere and going out through our outlet. We can also visualize the flow of streamlines over the sphere. Switch off the contour view. Click on Streamline. Click on OK. Start from plane 1. Click on Apply. Select the direction as backward and forward. Select the number of points as 150. Click on Apply. You can see the streamlines of flow over our sphere. Go to Color. Select Variable. Select the variable as Temperature. Select the range as Local. Click on Apply. Here you can see that the air is getting heated as it flows over our hot sphere. To clearly visualize this effect, select the range as user specified. Select the range from 300 to 305 kelvins. Click on Apply. You can clearly visualize that the air in the wake region behind the sphere has already been heated by approximately 5 kelvins. This clearly shows the heat transfer taking place between the cold incoming air and the hot sphere. We can also visualize the vectors. Switch off the Streamline view. Click on Vectors button. Click on OK. The location of our vectors is plane 1. Click on Apply. Here we can see the vector plot of flow over the sphere. To visualize the temperature vectors, click on Color, select Variable, Select the variable as temperature. Select the range as local. Click on Apply. Here you can see that the heat transfer phenomenon is not so evident. To view the heat transfer more clearly, we need to select the range as user specified. Select the range from 300 to 305 Kelvin. Click on Apply. We will use the sampling method as equally spaced. Click on Apply. Enter the number of points as 1000. Click on Apply. You can clearly visualize the heat transfer taking place when the cold air is flowing over the hot sphere. You can change the symbol type to arrow 2D. Click on Apply. Here you can see that the air is being separated when it hits the sphere while coming in through the inlet. If we visualize the velocity vectors, we can observe that there is a low velocity region just after the sphere in the wake region. This phenomenon occurs due to flow separation of the air when it hits the sphere from inlet. The air is split over the sphere and the velocity of the air is increased. The air travels so fast that it does not stop to go over the sphere, and hence in the wake region behind the sphere we get a low velocity region. We can also animate the flow by using the streamlines. Turn off the vectors. Turn on the streamline view. Double-click on Streamline. Click on Animation button. Select the streamline. Keep the speed of animation as slow. Click on Play button. Here you can see that the particle size is very large and inappropriate for visualization purposes. Stop the animation. We can reduce the symbol size by going in Options. Enter symbol size as 0.5. Click on OK. Click on Play button again. You can see that the symbol size has been reduced and now it is more feasible for visualization of the airflow. You can observe that cold air is coming from the inlet and getting heated as it flows over the sphere. Click on Stop. This is how we can simulate flow of cold air over a hot sphere by using ANSYS Fluent. That's all for today. We will meet again in a new video with a new simulation. If you have liked this video and found it informative, please share it with your fellow CFD colleagues. See you again in the next video. Goodbye till then.